Welcome to this really exciting presentation by Nicoló Brambilla, CTO of Nanoramic Laboratories. This is going to be a very exciting presentation because they have a very unique approach to creating a silicon-dominant battery, which is free of NMP and also free of PVDF. And the process is very interesting, so you will hear more. I know that the other session is still in the Q&A, so we will start very slowly, and then I think Nicoló will build up into the presentation. So as always, remember to ask your questions. Type in your questions on the right-hand side. We will ask all of your questions, and then if time runs out, you can meet Nicoló in the lounge to follow the discussions. So the stage is yours, Nicoló. As I mentioned, 2 minutes before the end, I will give you the heads up. Time is almost up.
Sure.
So yeah, you can start now.
Yeah, no, thanks. Thank you very much for introduction, and thank you all for listening to my presentation today. So today I will talk about our lithium-ion battery cells that we developed here in Nanoramic Laboratories with our unique kind of technology, which is called Neocarbonix at the core. The data that I will share with you today are data on lithium-ion battery cells, multi-layer cells with silicon-dominant anode and NMC 811 cathode that is made with an NMP-free and PVDF-free process. So we'll see what kind of advantages this kind of process actually brings, both in terms of the actual energy, power, but also cycle life, to the battery, as well as the cost part of things, which is obviously key for those kind of batteries. So to take a quick look at what Neocarbonix is. So basically, this is a electrode kind of technology platform where we have a 3D carbon matrix that is present in the active layers. So the active layer are the coatings that are coated both for the anode and also cathodes on top of the aluminum or copper foil. So that's what I mean by active layer. And this 3D carbon matrix has a dual function. It has the function of being the electrical kind of scaffold for that layer. So we actually achieve electrical conductivities that, especially in cathodes, we measure this to be between 10 to 100 times higher compared to a conventional composite of a PVDF binder plus carbon black. But that structure has also binding properties. And this is a key aspect, because when we have something that has high electrical conductivity and is uniform throughout the active layer, but also it has good kind of binding properties, that is why and how in the cathode we are able to completely eliminate the need for PVDF binders. So now, why that's so important? Well, this is important not just from let's say from a power performance point of view. Obviously, if there is no PVDF binder, the electrical conductivity is much higher. But this opens up a lot of opportunities also when it comes to the manufacturing process. Because as you all know, cathodes today are manufactured with a coating process that use NMP as a solvent. And the usage of NMP is only because there is a PVDF binder that really needs to be dissolved and needs to be stable in that type of slurry. So since we don't have those type of binders, we have a wide choice of solvents that we can use. So something that I want to clarify, since now our process uses a roll-to-roll coating type of system. So, we're still talking about a wet coating process that leverages those kind of machines. But the big difference is that we are NMP-free, and today we have two types of slurries. We have the water-based slurries for all our anode, including our silicon-dominant anode. And water-based slurry can also be used in some of our cathodes, including LFP, for example. But for those nickel-rich type of cathodes that are moisture sensitive, we have an alcohol-based type of slurry, which has a lot of advantages in terms of drying times. Obviously, those solvents can be dried at a fraction of the temperatures that are used to dry NMP. And also, it is possible to achieve thick kind of coating, so high mass loadings. And here I have high mass loading, greater than 6 million power per centimeter square per side of current collector.